So let's start at the very beginning. It's a very good place to start. When you read, you begin with A, B, C, and when you irrigate, you go drip, drip, drip. And so we're going to go back and talk about things that I'm sure a lot of you know, and a lot of the material that Mary Lou just covered. Thank you very much. But you know, I want us all to get on the same plane of understanding. And if you've got questions, you know, don't hesitate to ask, and Mary Lou can intercede and ask those questions. So Mary Lou, you know, made this point: a plant has to lose water in order to grow. The stomata have to be open to allow carbon dioxide to go in, and as a consequence, water is going to leave. And you know, water moving through the plant is doing many different things, not just creating a happy, healthy plant, but it's moving nutrients and it's cooling the plant. And it's not just cooling the leaf, it's cooling the whole stem. Water moving from the root, from the soil to the root through the stem is like a radiator. It's carrying the heat from the stem up through the leaf and out into the atmosphere. So, you know, we get sunburn damage when the stomata close, and the sunburn damage on a stem or a branch is because the water's not moving through the plant itself. So you got to keep water moving in the plant in order for it to grow. So here's the stomata that Mary Lou showed, opening and closed. And so water loss through stomata is called transpiration. And again, this is a movement of water that goes from the soil through the root, up the stem, out the leaf. And this is all driven through basically evaporation. We call it transpiration, but it's the same exact physical process of water moving from one area of high content to an area of low content. So there's a coleus plant, and there's the transpirational material that's condensing on the walls of the glass there. You know, coleus is a really great plant for showing water properties. It's, you know, it wilts when it doesn't get enough. It wilts when it gets too much. So you know, it's not just water. It's also air. So you know, the plants, we talk about plants growing in soil, but you know, it's a whole environment in the soil that they're growing, and they're growing where the nutrients are, where the air is, and where the water is, and everything's got to be just right for the plant to grow well. One of the things I've emphasized over the years is that we're not really so much as avocado growers into saving water so much, which is, you know, valuable. But, you know, if you don't get your water management right, you don't have a healthy tree, you don't have healthy production, you don't have good yields, you got a sick tree. So water management, it goes way beyond just water conservation. So evaporation is the same process as transpiration. This is an evaporation pan. This is how water use was estimated in the good old days. Yeah, this is how evaporation or transpiration, evapotranspiration was evaluated in the days before we had these automated digital systems that measure air temperature and humidity and sunlight, and this is quite accurate, but you got to be out there, and you got to keep the dogs from drinking the water, and you got to keep the birds from staying in there. And so effectively, water loss from a freely transpiring field of alfalfa or grass is very similar to the water loss that comes from the surface of water. So water is moving through the pores in soil, almost the same as it's moving through the pore, the stomata that is in the leaf. So we confound the two when when we're looking at water use, water consumption off a field, we're looking at not just the water coming off the leaves, but off the soil as well. So water loss from a field where crops are grown is called evapotranspiration, and this is really driven by sunlight in the plant. Okay, it's as Mary Lou showed, the stomata opening is really controlled by sunlight, and there's an optimum time of day when the stomata are open because there's optimum sun. And when we have overcast conditions, when we have short days, stomata are not as open and we get less transpiration going on. So the overriding factor for water loss as transpiration in a plant is actually the sunlight. And we often forget that. Along the coast here, we have these May gray, June gloom days where there's not a whole lot of sunlight and transpiration is way down, whereas along the coast in January, February, it may be a short day, but bright, clear blue skies, and we can actually have substantially more water demand in the wintertime than we can have in the spring. And so oftentimes, I mean, when I first came here from the Central Valley, I heard people saying, well, you don't need to irrigate in the wintertime. And I'm going, what? You know, you go out and you find dry dirt, and people would turn their water off. So evapotranspiration is actually driven by sunlight. Number one, sunlight, day length in the clouds. Wind, air, wind is really an important factor. Humidity, if you're in Hawaii or Florida where it's hot and humid and, you'd never dry out, that means there's no driving force for evaporation to occur off your skin. So when you have high humidity, you've got low transpiration, low evaporation. And then heat, and actually heat is the least important factor for driving evapotranspiration. Sunlight, amount of light is what primarily drives it. Then wind is so important. Humidity is really important. And heat is, of the four, the least important. And, as human beings, it's often heat that we respond to. Oh, it's a cool day, but man, if it's windy and the sun's out, it's bright and humidity is low, you can use a lot more water than on a hot day. So the thing is, these components that drive evapotranspiration are often interlinked. So oftentimes when we have wind, we've got low humidity, and so that compounds the effect of water loss in a tree. An interesting thing is that as climate changes, we used to get lots of fall Santa Ana conditions, and now virtually all of our Santa Anas are occurring in the wintertime when we have cooler temperatures, but man, stuff dries out really fast when the Santa Anas blow. So here is a trick question. Plants need more water in a sandy soil than they do in a clay soil. Okay, this is a trick question. And the point I'm trying to make here is that the soil is a reservoir of water. The driving factor for water loss is the environment outside the soil. It's the sun, the wind, the humidity, and it's the temperature. And all too often we hear this thing that, oh, I've got a clay soil, I've got to put on more water. No, you put on a lot of water, but you put it on less frequently. On a sandy soil, it has lower water holding capacity, so you put on less water more frequently. So the soil is a reservoir. It's not the driving factor that causes water loss. Trick. So this trick's going to come up some more. So evapotranspiration is driven by sun, wind, humidity, and temperature. And so that's why the California Irrigation Management Information System, the CIMIS system, works so well. It's measuring sun day length, how much light is arriving in an orchard to keep the stomata open and cause photosynthesis as well as transpiration. It's measuring wind, it's measuring humidity, and it's measuring temperature. So measuring the 4 major factors that drive water loss in a plant. What's this? Is there a question? Okay.
No question.
Okay. So the soil is the reservoir for water. Okay. So we got to separate these two, or no, we've got to integrate these two. We've got to link them somehow. And the plant is the link between the soil reservoir and the driving factor for water use in the plant. And so the soil is this matrix of particles. And we've got large particles and large voids, large pores in a sand. And in a clay, we've got small particles and small voids and small pores. There's actually many more volumes of pores in a clay soil. That's why it holds more water than in a sandy soil. So the pores are larger, they evacuate more rapidly in a sand. In a clay soil, there are many small pores. Water moves slowly through these small pores, but it actually holds more water. And we probably all know that. So in a saturated soil, the sandy soil is going to hold less water volumetrically than a clay soil will. And so one of the things about, the difference in textures of soils and there's a difference between aggregation and texture. Texture is the size and amount of particles. Aggregation is how those particles are arranged. And so you can actually have a well-arranged clay soil that's held together by roots and organic matter and the exudates that come from roots that actually can create some fairly large voids. And if you go there, this is a real common problem in annual cropping systems, corn, soybeans, where they go in and plow and plow and plow. They completely destroy the aggregate structure, and they completely destroy these larger pores that are formed by the roots. One of the beauties of avocados is that it's a stable system. It's one giant root. Once the trees are about 8 to 10 years old, or in normally planted orchards, and if it's high density, it's one big root system even earlier. But those roots create some fairly large pores even in a clay soil. So having a textural class that has high clay doesn't mean that you necessarily have no small pores, because through aggregate structure that occurs through the roots, the insects, the bugs, the glues that come from the roots, you can create some fairly large pores and create better water movement. Okay, so we have this condition of saturation. And saturation is the condition where there's no air in the soil. Okay, and roots need air. They need air as much as they need water. And when you lose air, you can send it, plant's going to shut down its stomata. It's going to stop losing water if it doesn't have air. And this is a commonly seen in a plant like coleus, an annual plant. If you saturate the root, it'll wilt. It shuts down, and you don't see that effectively in avocados. But we've had situations here where, gosh, back in, what was it, 1995, it rained 50 inches here. And we saw a lot of wilting in plants because there was no water, no air in the soil. It was all water. So when a soil is saturated, basically through gravity, water is pulled through. It's in a kind of balance between the surface tension of the particles and the pull of gravity, and slowly air is introduced into those larger pores. And you'll see that in the smaller pores, they're still saturated, okay, but the larger pores start emptying and you get air moving in. And so this is really an ideal situation for roots. They want air and they want water. So there's water in the smaller pores, and there's, you know, a film of water along the larger pores, but there's air in there as well. And this drainage that occurs, this water movement going from saturation, every time you irrigate, you saturate the soil. Every time you irrigate, you exclude air. Every time you irrigate, you asphyxiate the root system. And it, depending on the texture, a sandy soil has larger pores, it drains more rapidly, and it returns a condition of kind of a balance of adequate air and adequate water. In a clay soil, it takes longer. Usually after an irrigation, it takes about 3 days or so for a clay soil to have adequate air within the system to satisfy the roots. And that's why, you know, avocados are so sensitive to irrigation. You know, they don't like saturation. You know, you're dealing with the root zone no deeper than 18 inches, and a lot of times it's a foot. So you gotta, you know, every time you irrigate, you got to make sure that you get into a condition where there's adequate air again. So, you know, frequent irrigations really challenge the health of the root system. So roots need air just like we do. You know, they're respiring. You know, Mary Lou showed that respiration diagram where you need oxygen and glucose in order to create energy. And if you don't have oxygen, air, you basically asphyxiate the darn roots. And they don't like that. Avocados really don't like that. You know, one of the hardest things is to get a citrus grower to grow avocados. You know, they want to irrigate, you know, 48 hours and flood the system. And, you know, avocados just can't handle that. So here's an annual plant, which, you know, really more clearly demonstrates what happens when air, when the soil is saturated, there's no air, and you do get wilting occurring. Now, in a woody plant like avocado, you don't see it, you know, unless you have, you know, persistent conditions like we had in 1995, where every week it rained, and the soil's never dried out. And boy, then you saw wilting. And you'll see, I've seen this where, you know, an irrigation line breaks, or, you know, somebody's been irrigating their vegetables right in the avocado orchard, and they're watering the vegetables all the time. And finally, the avocados just get, you know, saturated, and they wilt finally. So when soil's dry, you get the same condition. So, you know, wilt can occur from too much water, which is exclusion of air, and it can come from lack of water. And so, you know, the water, you know, is what, it's 90% of the tree. You know, it's just, if you don't have water, you're going to wilt. So the amount of water held in the soil between saturation and what is drained is what we call available water. And, you know, this is probably the most common question I get. And I'll be frank, 80% of the problems I see in avocados, 80% of the problems I see in agriculture are water related, water management. It's too much, too little, the timing is off. And the simplest thing of going in and getting on your knees, brother, get on your knees and dig some dirt and put it in your palm and squeeze it around. And if it takes the shape of your hand, if it takes the shape of your palm, if you can see the the lines of your hand in the squeezed soil, there's adequate water for the plant. If you squeeze it and the soil cracks, it's time to water. If you squeeze it and water comes out, it's too much water. You know, and this works for any soil texture, you know, sandy soil or clay soil, the sand at the beach or the sand in the desert. You know, if you take the soil into your hand and if you can mold it, you can form it, it takes the shape of your palm, there's adequate moisture. Okay, and for years, you know, the irrigation schedulers, you know, use this technique. They did it before, you know, tensiometers. They did it 2,000 years ago. You know, it works. It works. It works. So plants use the available water around their roots. Okay, that's where it's immediately available. And then very slowly, water moves from where there is water to that dry region. So you get this zone of depletion right around the root zone. And depending on how depleted that area and how rapidly the water moves to the root, you'll get rehydration occurring. So again, going back to a sand versus a clay texture, the larger pores, water moves more rapidly when it's present in a sandy soil to the root than in a clay soil where the pores are smaller. So it slowly moves through the clay soil, but it eventually gets there. Now, the USDA used to have what was called the sunflower test, where they would put a plant, have a sunflower growing, and they'd water it, and the sunflower would grow and grow and grow. And then in a few days, midday, the sunflower would wilt. And then overnight, slowly water would move into the root zone from the surrounding area. And boom, in the morning, it was rehydrated and it looked fine. And then that afternoon, earlier, it would wilt. And then the plant would rehydrate during the day, during the night, and in the morning, oh, it was fine. And it would keep doing that until one day in the morning, it wouldn't perk up. And that was a measure of the water holding capacity of the soil. You know, so it was a very, very visual, although primitive, but very effective way of measuring available water in the soil. So, you know, I guess, you know, we could plant sunflowers out in the field too, and that would tell us when to irrigate. It would work just as well as a tensiometer. Okay, as time goes on, it takes longer and longer for water to move from the bulk soil to where those roots are, and eventually you'll get wilting occurring. And again, you know, this works really well. You know, if you've got weeds out in the field in an orchard, and it's hard to see that in a mature avocado orchard with all that beautiful mulch that's out there. But you know, just looking at your weeds tells you, you know, how wet or dry your orchard is. Really common measure of water condition of turf, of grass, is if you step on it and doesn't bounce back, oh, that thing's wilted, it's time to water. And so you can use, you know, visually out in the field, you know, don't just rely on CIMMYS, don't just rely on the soil moisture in your hand, just don't rely on what the plant, use everything, use all your senses to know when to irrigate. So how does water move in the soil? Water moves in a wetting front, okay? It moves down, and it's moving down energetically. It's not necessarily, you know, in general, it's moving gravitationally down, but it moves towards energy gradients moving down. So we're going to see how that works. So basically, water will move through a soil texture until it finds another soil texture. So layered soils are really hard to work with because water wants to stay in the initial soil that it starts in. So this can be a sandy soil that it starts in or a clay soil, but whatever the soil texture is it starts in, it will move through that texture until it finds another texture, and then it stops, and it stops and then backfills until there's enough positive pressure. It fills up all the pores. It saturates all the pores until it gets enough positive pressure to move into the next soil texture. So this is a diagram of what happens. It's water moves down, and then boom, it hits the next texture, and it stops and spreads out until it fills all the pores of that texture above, and then it will move into the next texture. So here, one of the worst things you can do is, these $50 holes that you plant for your $40 avocado tree. You don't want to make a huge hole. You want to make as small a hole as possible because you want your root system to get into that bulk soil as soon as possible. You want to create as little textural difference between the hole and the surrounding soil. You do not want to use a planting mix. The worst thing in the world is to put a planting mix into the planting hole of an avocado or an citrus or an almond or a walnut or any plant. Don't use planting mix. You want to get a small hole and you want to get those roots into the bulk soil because you want to avoid as much textural difference as possible. When you create a large hole with planting mix, you create this pot that fills up with water until the pores are saturated, and then the water moves out in the bulk soil. And the whole time that it's sitting there, the roots are going, I need air. So here is a real example. This is from the University of Washington. No, it's not. It's Washington City College or something like that. I forget where it's from. But you see how water moves down through these different textures, and boom, it spreads out. It doesn't move into the next texture. It's saturating the area up here, and I'm not sure what these textures are, but you can see that this is a real life example. Water wants to stay in the texture that it initially starts in. You want to make as small a hole as possible when you plant, and you want to be careful because those darn avocado roots are so delicate. But the hole's got to be big enough so you can get your hand in there to cut the liner and remove it. So water movement is controlled. Okay, it's controlled energetically. It's moving down an energy gradient. And so the energy gradient in the soil is often down. Okay, water is being pulled down by gravity. But it's also moving from a wet area to a dry area. Okay, so that example of how water moves to the root zone, it moves from the bulk wet area to the area around the roots where it's been dry. So water moves from a wet to a dry area. And here's an example of water moving up a gradient. So this is a paper towel that's in a red wine vinegar, and water is moving, or the red wine vinegar is moving up the gradient. The gradient is going from wet to dry. So water doesn't necessarily move down. It's moving from wet to dry, and it's moving from less salty to more salty. So it's, on a wet day, God forbid, if you spill your salt shaker on the table and you come back an hour later, you see puddles of water around the salt grains. Salt pulls water. So this is why salt is such a major issue in irrigated agriculture. The collapse of Mesopotamia is because of the salinity increase that occurred over several 100,000 years. Unless you can get salinity management occurring, you can put any amount of water on, and if you don't manage the salt, you're going to have a water deprived plant, because the salt doesn't want to go to the plant, or excuse me, the water doesn't want to go to the plant, it wants to go to the salt. So water is moving down, it's moving from wet to dry, it's moving from less salty to more salty, and it moves towards surfaces. And so this is why capillary rise is occurring. So water is attracted to surfaces. Water in the soil is attracted to the soil particles. Water is attracted to the largest area of soil surfaces, which are the small pores. Okay, so there's actually less surface in a large pore than there is in a small pore. So if you look at the combined surfaces in small pores for the same volume of soil, that's why clays hold more water. There's more soil surfaces. So water moves towards surfaces. It's interesting, clays are buffered. Buffering means tendency not to change, resistance to change. Buffering is holding on to water, holding on to heat, holding on to nutrients. A clay soil inherently has the capacity to hold more nutrients, more water, more heat than a sandy soil. So sandy soils are less buffered, and so they dry out faster. You have to put more frequent small nutrients on than you do on a clay soil. So the speed that water moves in the soil is largely controlled by the texture, how much sand or clay is there. And so we have, those are the extremes. Boy, you sure don't want to plant an avocado on clay, because it's so difficult to manage the air and water on a clay as opposed to a sand. And this is one reason why we plant on berms or mounds with avocados when we get onto heavier soils or on flat ground, is that when you create a berm, you create elevation, which means you create a greater influence of gravity, a greater pull. So there's a larger tendency to move and reintroduce air in a berm or a mound. But also too, a berm or a mound dries out a lot faster. So you got to manage your water more carefully. When you expose the soil, as in a mound, it's more exposed to wind and the conditions that drive evaporation. So the mound dries out faster. So clays have many more small pores that carry air and water, but it moves slowly. In the sand, the pores are bigger, but there are fewer pores. Remember, the clay holds more air and more water, but it just moves more slowly. In the sand, air and water both move faster in the sand. So with the same volume of water, here's an example. On a sandy soil, you put the same volume, it goes deeper than it does in a clay soil. So you probably all knew that. So this means that you don't want to put the same amount of water on a sand as a clay if you're managing it within the same root zone. So in a sand or clay, the tendency is to have a more shallow root system in a clay soil than in the sand. And that's because the clay soil, oh man, this gets complicated. Soils are wonderful. The nutritional properties of a soil tend to be much higher near the surface, because that's where the organic matter is. That's where the organic matter is turning over. That's where leaves are dropping and they're decomposing and they're releasing calcium, magnesium, iron, zinc, manganese, all that good shit. And so that's where the roots proliferate. Roots proliferate in a zone of optimum growing conditions, where the optimum water and air and nutrients are. We often hear this thing of roots grow towards water. No, they proliferate where there is water. They don't know that there's water 10 feet away. They don't know water is a foot away. You know, there may be diffusion of moisture that they can sense, you know, when it's, you know, again, water is moving towards a dry area. So if there's adequate flow of water coming, then, you know, the root's going to be happy, but it's not going to grow towards water. It proliferates where there's conditions that optimize growth. And so if you put the same amount of water onto a sand as a clay, you're going to get different water movement. You know, and you know, on a sandy soil, if you put a lot of water on, you're going to be leaching all those nutrients down. So you got to manage the water differently. So generally speaking, a sandy soil you water frequently with small amounts. And if you have Santa conditions, you may water, you know, once a day or something like that, just to keep up with the reservoir being pumped dry by the transpiration going through the leaves. Whereas in a clay, you might be able to get by with 2 or 3 days because there's adequate water and the water is moving rapidly enough to meet the transpirational demand. So back to this idea, the sand and clays are holding water, they're reservoirs, and that's all they are. They're not, the driving factor is the surrounding environment. Okay, water is held in a clay soil more than a sandy soil for a longer period of time. And then how the wetted pattern occurs, again, going back to how water moves, it's moving down. Okay, so it does what's called stovepiping. You know, stovepipe, what's that? Anyway, it moves straight down in a sandy soil because gravity has a much greater influence than the soil surfaces, the particle surfaces that are in a clay soil. In a clay soil, the soil surfaces retain water. They hold water against gravitational pull. So water moves differently. The pattern of water is different in a sandy soil versus a clay soil. Okay, moves laterally in a clay soil much more so than a sandy soil. So if you can imagine, when you lay out your irrigation lines, you know, you're going to have to space your emitters much more closely in a sandy soil than you would in a clay soil. And so, you know, we get these ram tubings which have built-in emitters that are wonderful. You put 2 lines out and, you know, you can get by with a fairly wide spacing between emitters on a heavier soil, you know, 2 feet apart between emitters on a heavier soil, whereas on a sandy soil, you might want to space them about every foot apart. Okay, so soil texture is going to determine the spacing of the emitters, but it's also going to determine kind of the root architecture. So if you can imagine, again, roots proliferate in a zone where the conditions are optimum. So if it's dry out here, okay, this is California, it doesn't rain, the roots are going to be in this zone. Where's my pointer? The roots are going to be somewhere in this zone where it's wet and there's adequate air, okay? And so you're going to get a much wider spacing of roots in a heavier soil than you would in a sandy soil. Roots tend to function when there's water, and when the soil dries out, they go through a kind of dormancy. They don't shut down altogether, but they, you know, and again, in a mature orchard, you got roots everywhere. So the tree right here may have roots 2 rows over. You know, avocado's got a huge rooting system. So you might find that if you turn the water off on a row of trees, that the neighboring trees might start wilting. Well, those roots were spread out into that other row, and they were tapping into the water that was coming out of that those emitters. So here's that question again. Plants need more water in a sandy soil than they do in a clay soil. No, it's the driving force. It's, it's the surrounding, it's the sun, it's the wind, sun, wind, humidity. When it's dry, it's Santa Ana's, and the sun is bright and clear and the sky is blue, the tree is pumping water out. And it may not even be hot. It may only be 80 degrees or 75 degrees, okay? Okay, look at the sun, look at the wind, and look at the humidity. And then consider how hot it is. Okay, the soil is a reservoir, and it needs to be refilled at in an adequate fashion to meet the transpirational demands of the tree. Sandy soils need more frequent small irrigations than a clay soil. Okay, coarse textured soil needs frequent small amounts of water and nutrients, much more so than in a heavier soil. Putting the same amount of water on a sandy soil as a clay soil will push water more deeply in a sandy soil. You've got to irrigate soils differently according to the rooting zone, okay? So if you figure, you run your irrigation line for 5 hours, 10 hours, 15 hours, 24 hours, God forbid. And what is the depth of penetration that you're getting? Go out there with a piece of rebar, go out there with your soil tube. What depth of infiltration do you get with a given time of irrigation? Are you getting 6 inches? Are you getting 12 inches? Are you getting 18 inches? Are you getting 4 feet of infiltration? I was out looking at a citrus orchard not long ago on drip irrigation on sandy soil, and they were irrigating for 24 hours with drip. On drip, they were getting 3 feet of penetration. Golly, drip's not supposed to do that, but if you run it too long, it will do that. So figure out what depth of infiltration you get. And, this is a balancing act because, we've got salinity, this is a real problem. So you've got to apply enough water that you're getting leaching. And, this should be a whole lecture as well on, how do you leach? I mean, there's a lot of different ways of doing it, but, you've got to put enough water on at some point that you do get leaching, but you want to keep the water basically and the nutrients within the root zone. So at an irrigation, you don't want to get any deeper than about 18 inches of infiltration of water. So figure that out, run your system. You might have to do it 2 or 3 times, but after that, you know that, the pump is going to be running at a certain PSI and that, or you're getting water coming through your meter and at a certain flow rate, at a certain flow rate on this 5 acres or 10 acres or 20 acres, after 8 hours or 10 hours or 12 hours, you get this depth of infiltration. Boy, once you get that knowledge, you know how long to irrigate. Okay, this is really important. I guess everything's important. But water moves as a wetting front. It moves down with gravity. It moves basically from wet zone to a dry zone, and it moves in a wetting front. So everything behind this is exclusion of air. This is all saturated. There's no air. Roots don't like that. So the more frequently you irrigate, the more frequently you exclude air, the more frequently you create conditions for root rot. It's all integrated. You've got to keep a health. The most important thing you do out there is irrigate. If you don't irrigate right, you just, oh man, go back to the office and forget about farming. So when we have drip irrigation, when we have micro sprinklers, there are these areas, bulk soil, where there will be air, and air will move from the bulk soil into this zone of saturation, but it moves very slowly, and so frequent irrigations can cause problems in a plant. And you know, this thing about irrigating 10 times a day is really harmful for a plant. You know, you got to keep up with transpirational demand, atmospheric demand. But the less frequently good drink of water a plant gets, the healthier that root system is going to be. And you know, every time you irrigate, you cause a mini death of roots. And so here's an example. These are container plants, and it shows you the roots proliferate along the margins of the container. This is where the air is. You know, you're putting the water here, water comes down, and you know, eventually this whole thing is going to be filled with roots. But oftentimes when you look at a container plant, you'll see that a zone in the inside where there are no roots at all. And that's because that's the zone that's being saturated all the time. You know, the roots are where there's water. Where's my pointer? The roots are where there's water and there's air, and presumably there's nutrients. Okay, roots want optimum air and water. Okay, so we're talking about leaching to a certain extent, and you know, California in general has, well, no, that's not true, but Southern California in general has poor water quality, unless you're getting good sweet water out of the Feather River, and you know, even that picks up chlorides or sodium as it's coming down. I know pretty much along the coast, you know, we're dealing with well waters, and you know, anything that comes out of the ground is going to have salts in it. And you know, fortunately, much of the salts that we have north of LA, north of Los Angeles, are salts that are dominated by calcium and sulfate, which are beneficial salts. We do have saltwater intrusions coming from the ocean. We do have chlorides. I know down in the Colorado River area, chlorides are an issue. So wherever we put our water, we're putting salts on. It's one of the necessary evils. You know, every time we irrigate, we're putting salts out. And how water moves is going to determine where those salts go. And as Mary Lou pointed out, water is the universal solvent, and all the nutrients that a plant needs are in water. So one of the first symptoms of under irrigation is the plant turns yellow. And that's because, you know, it's not getting nitrogen. The water is carrying the nitrogen. So when a plant doesn't get adequate water, you know, it shows water wilting symptoms, but pretty rapidly it'll show nitrogen deficiency symptoms. Nitrogen is the #1 nutrient that a plant needs, and so that's one of the first things that shows up. Then you'll see potassium deficiency showing up. So wherever water moves, it carries nutrients, which are salts, and many of these salts are harmful, and even too much fertilizer is a salt and it's harmful. So, you know, overloading a system with fertilizer is not good because you're going to get a salt effect. So wherever water moves, okay, and again, water is moving down through gravity. It's moving from wet to dry. It's moving from less salty to more salty, and it's moving up a gradient through capillary rise, which is really the effect of soil texture. So we got to keep water moving through the system, through the root system, partly because we want to keep hydrating the roots, but also to keep the salts beneficial as well as toxic salts moving as well. So here's an example of a drip system. This is above ground drip, and this is in grapes, and the drippers are right here, and you see the water dripping down here. And so water moves out from that wet spot to the drier spot, but now it's carrying the salts and the water is moving actually towards the dry spot and it's being pulled by the salts now. So every time you irrigate, in this case, they may be putting fertilizer on as well, but they're putting salts on, and the water is going to move away from that wetted spot towards this what I would call dry spot, which is dry because it's salty. Okay, water is being pulled there by the salts. It's being pulled there by it's being the drier spot. But actually, at some point, it's gonna, if you go through over here and you take a glob of dirt and squeeze it, you may find it's really wet, and that's because the water is being pulled away from the root system towards those salts. So the more water is applied, the more nutrients are needed to be applied because you're pushing it out. So there's this balance that you've got with the nutrients that you're putting on that you want to go into the plant, and the salts that are in the water. The necessary evil that we do is irrigation. We're putting salts on, and we got to manage those salts. So a certain amount of water needs to be applied in excess to control salt. And avocados are very, very sensitive to salt, sodium, chloride specifically. So you can have actually a low salt content, but if you have a high sodium or high chloride content, you can see damage like this. So we have this generic salt effect, okay, from too much overall salt. And again, the salt can be a fertilizer. Or we have what's called the specific ion effect, where the avocados react specifically to sodium and chloride. So it's not uncommon to find waters that are relatively low in total salts, but they could be high in sodium or chloride, and you'll get salt damage like this. And you need to leach in order to create an environment, a root environment that doesn't see that salt or sodium or chloride. So what do you do? So first of all, you got to go through and fix your irrigation system. You got to make sure that irrigation system is putting out exactly what you want. And we're going to have speakers later on in this series that talk about how to manage an irrigation system, but getting the right distribution uniformity where every emitter is putting out the right amount, the same amount, as similar as possible, so that when you irrigate, you know that you're getting a wetting front that's moving down uniformly or as uniformly as possible through that root zone, so that you know how much water is being put on. You don't want to have one emitter, and this is really common with micro sprinklers. You go into an orchard and you hear buzz, 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 and they're putting out different amounts. One's clogged, one's jammed with a piece of a branch. You can hear that the system is not uniform, and you got to make sure that the system is uniform before you can manage a healthy orchard, before you can manage salts, before you even know how much water you're putting on. So you need to know how much water you're putting on, and you need to have a meter. There's still a lot of growers that don't have a meter or a meter that works. So a flow meter will tell you, is there a break out there? If you're getting more flow in a given time than should, you know that you've got a broken line somewhere. And if you're not putting out as much, you know that you've got a clog somewhere. And then you need to adjust the irrigation according to the needs of the tree. And you do this based on, as many factors as you can use. You use soil moisture measuring devices, you use your sensors, you look at the tree, you take your soil tube out, you take your shovel out, you use Simus, you figure out how wet that soil is and how rapidly the tree is pumping water out. And then you need to figure out what the leaching fraction should be. And you can do this with meters. You can take soil and take that and measure soil salinity. Anyway, so again, the most important thing that any grower does in irrigated California agriculture is managing their water. And it really affects the toxicities, salinities, it affects the deficiencies, it affects disease. You know, this is a condition that I found out in Fillmore. It was a citrus grower that was over irrigating. This is what asphyxiation looks like in avocados. This is Botryospharia. This is Botryosphaerias are so common in avocados, and it's really a reflection of irrigation management. If you're seeing white canker showing up on the branches of trees, it means there's something wrong with water management. This is an example of leaf and stem Botryosphaerias. Water management is going to affect not just diseases, but also pests. And, you know, in this day and age, I just saw the weather report out from Green Sheets saying that we're heading into June and there's going to be some hot weather ahead, and getting water management down is really important. You're going to, you know, control the heat and potential damage to leaves, fruit, and branches. And then it affects tree growth and yield. So the problem is it's often difficult to distinguish between too much water and too little water. And so, you know, this is something that you learn with experience. So irrigation is the most important job in the field, and don't wet the trunks. You know, we got to get our trees going, and, you know, you want to make sure water is at the base of the tree, but fairly soon after orchard establishment, you want to move the irrigation lines off, the water off the trunks, because we have a real problem here with Phytophthora, which used to be called Citricula, but it's a crown rot, and virtually all trees, not just avocados, you know, wetted trunks lead to a variety of crown rots, and avocados are really prone to Phytophthora named after John Menge, who did a lot of research on it. And you see it on the wet side of the tree, and if you're along the coast, if you have a lot of fog, you'll see it on the north side, which dries out less fast because the dew that accumulates on the back side of the tree. So, and you want to start moving your irrigation lines around in the winter time when we have rain. So, you know, moving into summertime, you don't want to change your irrigation pattern now, because the architecture, the root architecture, is adapted to the wetted pattern that you have now. The root system is adapted to the wetted pattern you have now. And if you start moving the emitters around right now, you can change the wetted pattern. And if the orchard is relatively young, you're not going to have roots everywhere, and you may cause stress in the tree. So I think that's it. Yeah, that's it.